What have the industries that make wine and hand sanitizer got in common? The first takes grapes soaked in sunshine in beautiful vineyards and turns the juice into red and white wine, a £1 billion industry every year in the UK. The second is an industry that makes gels used in hospitals to kill bacteria and viruses, something we're all now familiar with. Give up? Well, it is actually pretty simple. They both rely on ethanol. The size, polarity and the functional group it contains enable ethanol to be an everyday familiar compound. Let's work out why. This is Think 4. Throughout the higher chemistry course, you will have come across familiar and not so familiar functional groups, a part of a molecule that determines chemical behaviour. Recognising a functional group is the first step in determining the physical and chemical properties of a compound. It will also lead you into thinking about the reactions and the substances that are associated with it. Let's go on a journey, starting with ethanol, and make a number of connections along the way. Ethanol contains a hydroxyl functional group. Due to the small size of the molecule, ethanol can dissolve in water by forming hydrogen bonds with it. This leads it to be used in making alcoholic drinks. The size of ethanol also means it is very volatile and flammable. As ethanol only contains 2 carbons, it can only be a primary alcohol. If we oxidize the ethanol by removing the hydrogen, therefore increasing the oxygen to hydrogen ratio, we can produce ethanal, an aldehyde. This molecule contains a carbonyl group at the end of the chain. This is different from a ketone, which has a carbonyl group in the middle of the chain. By continuing to oxidize the ethanal, this time adding oxygen, we can obtain ethanoic acid, a type of carboxylic acid containing the carboxyl functional group. Carboxylic acids can be reacted with a base in a neutralization reaction. Vinegar has a high concentration of ethanoic acid. By reacting ethanol with a carboxylic acid, we can produce an ester and water. This reaction is a condensation reaction. This type of reaction is also used when linking amino acids together. The amino group of one amino acid reacts with the carboxyl group of another, forming a peptide link. Many of these amino acids joined together forms a polymer called a protein. Esters contain the ester link and often have a pleasant smell. This leads them to be used as fragrances and flavourings. Due to the low polarity of esters, they can be used to dissolve non-polar substances such as caffeine from tea. Everyday types of esters are edible fats and oils, formed through the reaction of a glycerol with long-chain carboxylic acid molecules. The appearance of multiple carbon-to-carbon double bonds in the fatty acid determines if the molecule is a fat or oil. If we were to break an ester back into the alcohol and carboxylic acid, we would go through a hydrolysis reaction. By putting a fat or oil through alkaline hydrolysis, we form an ionic salt, also known as a soap. The hydrophilic head and the hydrophobic tail of a soap molecule allows it to be useful for cleaning purposes. From one starting point, in this case ethanol, we can cover a lot of ground. It serves to highlight how and why chemistry is so connected, and understanding this is an important step in higher chemistry. Try this yourself, maybe using a mind map. Add specifics such as type of oxidizing agents, examples of ester names. Making all these links helps us see how chemistry is involved in so many things, from fighting pandemics to powering our future. And, of course, to making fine wines, something I take particularly seriously. Cheers! This was Think 4. Thanks for watching.